Go. Okay, from your notes, you'll notice that there's a definition of a sequence. A sequence is essentially just a number pattern, and there's specific for specific terms of a sequence. For instance, in this sequence, this is an arithmetic sequence. It's an arithmetic sequence because you add 3 each time. Right? Add 3 each time. What you'll also notice is 11. 11 is the 4th term of the sequence, or we can denote that as a sub 4 is 11 to reference the 4th term of the sequence. If that makes sense. The term value is 11. The term number is 4. When we write a sub 4 equals 11. This one, number 1, is actually a finite sequence, whereas number 2 is infinite, because the dot, dot, dot are at the end. Number 3, infinite or finite? Finite, because it stops at the end. Even though there's a dot, dot, dot in between, that doesn't necessarily mean that it goes on forever. That just means it didn't feel like writing all the stuff in between. Okay, if the dots are in the middle. If they're at the end, that references whether it's infinite. That shouldn't be too crazy for you. We talked about, you saw a video talking about an arithmetic sequence, which means there's a constant value that each term changes by. That constant value is called the common difference, or we refer to it as D, being the common difference. Okay. For instance, in number 1, what's the common difference between it? 10 to 6 is minus 4. Be minus 4. Minus 4 each time. Okay, and there's a little typo on the notes. That should be a 44. But the common difference on number 2 is plus 16. So D for this one is 16, and D for the first one is negative 4. Does that make sense? Yeah.
What was K?
K is just a variable. We're going to use a variable n instead, referencing the term number. K refers, in the video, references the term number, which I don't know why you used K, because number starts with an n. Anyways, what would the graph look like in an arithmetic sequence? To take a picture, or to get an understanding of what the graph looks like, if we make a table, an XY table, because you can graph anything with an XY table, except for the fact that we're no longer dealing with X's and Y's. We're dealing with term numbers, right, which we're going to affectionately call n to refer to number. And we deal with term values, which we're going to denote as a sub n. Okay. So in the first sequence, we have term 1, which is 10. We have term 2, which is 6. Term 3 is 2. Term 4 is negative 2. And term 5 is negative 6. One thing that you need to pay special attention to is these sequences, the domain of these sequences is only the natural numbers, or from the set of natural numbers. If you remember what that is, that's 1, 2, 3, 4, 5, 6, 7, 8, the counting numbers. Okay, there is no such thing as term 2.5. That makes no sense. Term number 2.5, that makes no sense for what we're talking about. So the domain, the numbers that you can put into the equation that we have, are going to have to be integers. Actually, I need to make special note that it's for negative 2, not for negative 4. Thank you for that. So when we go ahead and graph this, what does it look like graphically? We have 1 and then 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, not enough space. Oh well. And then 2, 6, 2, 1, 2, 3, 4, 5, 6. 2, 6, 4, 3, 2, 4, negative 2. What does it look like graphically? Where does it look like the dots are going together? As 1, 2, 3, 4, 5, 6. They look like they're headed together as a straight line. arithmetic sequences are linear. Although we can't connect. Don't connect. Don't connect the dots, because if you connect the dots, that references, like if I put a dot right there, or I put a line in between these two dots, like that, that references the fact that all those ordered pairs that are on that line work for this equation or for this sequence. That's not true, because we only have the counting numbers that are allowed to work for the sequence on the x-axis or on the n-axis in this case. That would be the n-axis. This would be a sub n. All right. Next one, there's a geometric sequence where there's a common ratio r. Okay, r references the multiplier, what you multiply each term by to get to the next one. Okay, that's what the common ratio is. So like on number 1, what's the multiplier? Multiply by -3 each time. Times it by -3 each time. So r is -3, and this is a geometric sequence. On number 2, what's the multiplier? What do you multiply by? Not 4. You're thinking divide by 4, so you need to talk about in terms of multiplying, because the ratio is what's multiplied. Okay, so it's times 1/4 each time, not divide by 4. So it's times 1/4. Okay, each time. So now to get a picture of this one graphically, we're going to take a look at number 2, because it'll be easier to graph. So if we look at the, oops, it's not x and y, remember it's n and a sub n. So the first term was 8, the second term was 2, the third term 0.5, the fourth term 0.125. So if we graph those points, 1, 8, 2, 2, 3.5-ish, 4, 1.5. Anybody know what shape that's looking like? This one's actually of an exponential model, where the domain is restricted to the integers. Now the range of this can be anything, so you can have decimals if you want coming out in your range. It's just what you put in. You can't have decimals or fractions. All right, so some problems here. By the way, in your notes I redid this one and redid that one last minute because I wanted to represent it a little bit differently to you. Okay, so make those changes. But anyways, is this sequence finite or infinite? That means it goes on forever. The dot, dot, dot at the end. It's infinite. Why would I rewrite? A sub 5, if I want to find a sub 5, that refers to the 5th term, which in this case, 1, 2, 3, 4, we have to find it. Right? Are you going to find it? You have to figure out whether it's a ratio or a difference or what the pattern is, essentially, and then you just keep that pattern for now. What's the pattern? Plus 7 each time? So 25 plus 7 is 32? Okay. Since it's added to 7, we know that it's an arithmetic sequence each time. It's an infinite arithmetic sequence. So a sub 6, the next term. A sub 6, the 6th term after that, or the 6th term, which would be 7 more, would be 39. And the 7th term, 7 more, would be 46. Right? Sweet. Next problem. What type of sequence is it? By the way, can you identify that right away? It's finite, yep. Find a sub 8. So we want the 8th term, 1st, 2nd, 3rd, 4th, 5th. We got to keep going, right? So what's the change in this pattern? Multiply by 2 each time. So that means the common ratio is 2. And this is a geometric sequence, right? Finite geometric. There are dot, dot, dots in it, but they're in the middle, and there's an end number, 40, 96. So what would the 8th term be if we keep the pattern going? What would the 8th term be? A sub 8 is 512. Yep. Now here's the deal. If by the way, this is kind of interesting. This is 2 to the x plus 1 power or n plus 1 power, the closed form of this. If you guys are familiar with computer language and computer memory values, that's a very common computer memory value. This is also 40, 96, 32, 16, 8, 4. Those are all different things. Those reference the amount of combinations of ones and zeros in binary code that allow you to get there. So when somebody says like it's 512 megabytes, that means there's 512 megabytes worth of combinations of the ones and zeros that can go into that memory. Anyways, all right, go through and work these guys. So what's the common? What type of sequence is the first one? Nope, it's geometric. Geometric, and I'm not projecting for you guys. It's geometric. It's geometric because the ratio is -1/2. Multiply by -1/2 each time. B, add 4 each time. This is arithmetic. And then the difference is 4. Number 3, C, rather, the third one. This one's neither. Even though it switches back and forth kind of in each term, it doesn't fit either of the models. D, what is it? It's arithmetic. What's the difference? -7. Add -7. This guy, geometric, and the ratio is 3. That guy, let me get you your homework too. That's your homework.